This is 338 data compression. We've got sound files are stored as bit patterns. Bit patterns are often compressed. Compress the following bit pattern using run length encoding. So run length encoding, what we do is we count the number of bits that are the same and we join them together into data pairs. So we've got 1, 2, 3, 4, 5, 6 zeros. So I would write 6, 0. I'm just going to cross those off so that I know that I've done them. Then we've got 1, 2, 3, 4, 5, 6, 7 ones. So I would put 7, 1. Then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros. And then I've got 1, 2, 3, 4, 5, 6, 7, 7 ones. So that is the compressed version using run length encoding. And I get 4 marks there. So I'd imagine I'll get 4 marks for each one of those being correct. Now I've got shade 1 lozenge, which shows the true statement about run length encoding. So look at all 3 to figure it out. It will always make a file smaller, not necessarily. Okay? Because if you had 1, 0, 1, 0, 1, 0, 1, 0, you couldn't just put, there'll be 1, 1, and then there'll be 1, 0. So it wouldn't make it any smaller there. So it is most effective on data that appears random. No, it's most effective when there's loads and loads of ones together and loads of zeros together. So that's not going to be accurate either. It will not lose any of the original data. Yeah, that's the correct one, because using run length encoding, it is a lossless compression, which means that it doesn't lose any of its original data. So I'll just shade that lozenge there. So the next one is all about Huffman coding. We've got when data is stored in a computer, it is often compressed. One method that can be used to compress text data is Huffman coding. To produce a Huffman code, each character in a piece of text is placed in a tree, with its position in the tree determined by how often the character was used in the piece of text. A Huffman tree for the text, Zoe saw a zebra at the zoo, is shown in figure 3. So it gives you the Huffman tree in the exam paper. Using this Huffman tree, the Huffman coding for the character E would be the bit pattern 110. So let's just see what they've used here. They've gone right and they've used 1 for right, because you don't have to do that, but that's just the standard. So they've done 1 for right, so that means that they must have done 0 for left. So they've gone 1, 1, 0 to get to the E. So 1, 1, 0, right, right, left. Okay, so that just is worth just double checking that, just in case it's swapped round, but it's most likely going to be that order in the exam. So the character Z is represented by the bit pattern 0, 1, 0, because from the top of the tree, Z is to the left, then right, and then left. Okay, so we've gone 0, 1, 0, 0, 1, 0. Okay, now it's asking us a question about it. So using the Huffman coding figure 3, complete the table to show the Huffman coding for the characters 0, space and B. So I've just got to use the same method again now to work out what these codes are for the dictionary. So 0 is here. So I'm going right. So that's 1, right, right. So I've gone right 3 times. So it's 1, 1, 1. Space is here. So I've gone right and then I've gone left. So it's 1, 0. B is there. So to get to B, it's quite a long way down. I go left, left, right, right, left. So left, left, right, right, left. Let's just double check that. So left, left, right, right, left, 0, 0, 1, 1, 0. Yeah. Okay. And then we've got Huffman, using Huffman coding, the text Zoe saw a zebra at the zoo can be stored in 83 bits. Calculate how many additional bits are needed to store the same piece of text using ASCII. Show your working. Now, this one, it's saying additional bits. All right, so don't just put how many bits, put how many additional bits. So, you know that ASCII, each character stored is 7 bits. And then you've got to count each character, including the spaces, are used here. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So it's 26 characters. So we have to do 26 times 7. So if I do 7 times 20, and then I do 7 times 6. So 7 times 20 is 140. 7 times 6 is 42. I got that right, son? 7 times 6 is 42? Yeah, okay. And then we add those together to make 182. Okay, now going back to that question, it says how many additional bits? So we had 83 and it wants to know the additional bits, so I've got to do 182 take away 83 to give me the additional bits, so that would be 99 bits. So 99 additional bits is the correct answer, and I've shown my working as well, so I'd hope that I would get the 3 marks.